this video I want to explain the concept of the vector product or cross product, and let me firstly just say that it's going to be a product of two vectors which produces a vector result. So we've already got a product that's defined between two vectors, which is the scalar product or the dot product, and we know that that produces some sort of scalar result when we do A dot B, as long as A and B are non-zero. Now we're going to define the vector product, and the reason it's called a cross product in much the same way as the dot product is called the dot product is because we use a cross or a multiplication sign as the symbol for this type of product. And as I say, this is going to produce a vector result. So this is going to produce another vector. So here is the definition of the vector product in a sort of geometric sense. So let me write it first of all and then explain it. So it's going to start off looking quite like the dot product in geometric form. So A cross B is the magnitude of A times the magnitude of B. This time it's times the sine of the angle between them rather than the cosine. So looking pretty similar to the dot product at the moment, and at this stage all of those are scalar values. So what we need then is a vector which is going to give it a directional component. And so in the geometric definition I'll just write that as unit vector n, which is giving it direction. Alright, so let me try and explain this geometrically and then also talk about the different parts of that definition. So what I want you to try and picture is some sort of plane surface. Maybe this is just, lying horizontally. And we've got a couple of vectors lying on this plane or in this plane. So let's call that vector A, and this one here is vector B. Now if we take the cross product of those two vectors, well, let's start off by sort of bringing them together, if you like, so that we can see them tail to tail like that. And that gives us an angle theta between them. Well, the cross product is going to be another vector, and the vector is going to be perpendicular to both of those. So the vector that we get, which is the cross product, let's try and make that, I think that looks roughly perpendicular to both of those. So perpendicular to B and perpendicular to A. So that is A cross B. So if you can sort of imagine maybe that plane is horizontal, it's lying on the page so that A and B are both vectors on the page or on the table, then A cross B is going to be sticking directly out of the page at right angles to that page. And it's in a right-hand sense. So I know in physics there are a number of sort of phenomena which are described by right-hand rules. So if we curl our fingers in the direction from A towards B, so take the angle theta and curl the fingers of our right hand around in that direction, then our thumb will stick up out of the page, and that will be the direction of A cross B. Because the other possibility is that it could be down this way, but that would be kind of a left-hand rule, or that would be B cross A. So we'll talk a little bit more about that. Let me maybe just try and grab a little image here to demonstrate the right-hand rule for this one. So here's a little image of right-hand rule for cross product or vector product. So we've got our angle theta here between vector A and vector B, and curling the fingers of, so those fingers there are being curled around in the direction from A towards B of angle theta, and the thumb then of that right hand is pointing up out of the page. Now if we were talking about B cross A, then we would actually have that in the opposite direction. So I don't know whether you can picture this, but if we were going B cross A, then we'd need our fingers of our right hand to be curling around that way, which means you'd sort of need to flip your hand over the other way, and the thumb would point downwards. So A cross B and B cross A are going to be vectors which are equal and opposite in direction. But we can talk a little bit more about that as we sort of go through and do these in class. All right, so we've got our direction of our. Let's get rid of that there. We've got our direction of our vector. So what we've got in this definition here is we've got a part here which gives us the magnitude. Okay, so that bit there, the magnitude of A times the magnitude of B times sine theta, that's giving us the magnitude or length of this vector, and then that component there is giving us the direction. So let's just say where that is the magnitude of A cross B. In other words, another way of saying that would be actually to write it as magnitude of the vector product is equal to that. So that would be a shorthand way of saying that. And n with that little hat on indicating that's a unit vector. So n is a unit vector perpendicular to A and B in a right-hand sense. All right. So let's think about some of the things that this means for taking cross product or vector product of some common vectors. So let's start off with the unit vectors I, j, and k. What happens if we start taking some vector products of those? So what if I went something like I cross I? Well, that would be magnitude of I times magnitude of I times sine of 0 n. Well, the only thing that really matters out of all of that, because magnitude of I, well, each of those magnitudes there are just going to be 1, aren't they? So it's going to be 1 times 1 because they're unit vectors. But sine of 0 is 0. So what happens if we get 1 times 0 times n? So basically we're going to get a vector with magnitude of 0. So I'll write it as the 0 vector, but really it's just a vector with no magnitude. So anytime we take and that's true then for all parallel vectors. So true for all parallel vectors. That the cross product of any parallel vectors is going to be 0 in the same way as the dot product of any perpendicular vectors is 0. Except in this case, technically it's the 0 vector. What about if we took the cross product of, let's say, I and j? So that's going to be the magnitude of I times the magnitude of j times sine 90. And then we want it times a unit vector which is perpendicular to both I and j in the right-hand sense. And in fact, that is the vector k, isn't it? Because the z-axis is perpendicular to the x and y-axes in a right-hand sense, and k is a unit vector. Now each of these here, that's 1, that has a magnitude of 1. Sine 90 is equal to 1, so it's 1 times 1 times 1 times k, so it's just equal to k. Alright, so anytime we take the, let's sort of draw that as in a diagrammatic sense. If I take the cross product of I with j, that is going to give me the result of k. Okay, so cross product of I and j gives me the result of k. If I take the cross product of j and k, in that order, j cross k, using this same logic here, j cross k would result in the unit vector I. And if I took the cross product k cross I, that would give me the unit vector j. So hence drawing that little sort of circle there, which is indicating that sort of circular pattern there. if we then extended that, we could actually show that if we expanded out, so if I use that to expand a cross product in component form, to expand cross product in component form, so sort of distribute the cross product across all of those. So let's say that was in component form was A1, A2, A3, and B was B1, B2, B3. I could in fact show that this results in this here, A2, B3 minus A3, B2. So that would be the I component of the resultant vector. I would then get A3, B1 minus A1, B3, and finally A1, B2 minus A2, B1. Now you might say, how on earth do we remember that? Well, the good news is with both of these definitions of the cross product, you do not need to remember them because they are on your formula sheet. And there they are. So vector or cross product in sort of geometric form, there it is there, and there it is in component form. However, the other good news about this thing here is it's actually quite easy to establish this pattern just by working with those there, and I'll sort of show you that using an example. Okay, now I did kind of jump a long way by saying we can expand the cross product in component form. So what I mean by that is if you wrote this out as, you know, A1i plus A2j plus A3k times B1i plus B2j and so on, and then did, you know, this one crossed this one, and this one crossed the next one, and this one crossed the next one, and then this one crossed with each of those, and sort of expand them out like we would any other product, then all of those terms would end up with, you know, i's crossed with i's, or i's crossed with j's, and so on. We could use this definition here, where is it, up here, we could use that to find out that each of these terms becomes either 0 or becomes an I, j, and k term. And these are the I, j, and k terms we're left with. So I'm not going to go through all of that because it is a fair bit of work, but it's not actually that difficult to do if you'd like to try. So why don't we do an example now? I might just scroll down a bit here so I've got a bit of space, but let's do an example of a cross product. So I'm going to go to the exercise there, and let's pick the very first question. So we've got a vector A, which is I minus 4j plus k, and a vector B, which is 4i plus 3j. Alright, so the k component for that one is obviously 0. So if I'm doing A cross B, I'm going to write these in column vectors because they're a bit easier to work with that way. So 1, negative 4, 1, cross 4, 3, 0. Okay, so how do I get those components? Well, I can go to my formula sheet and use my formula as it stands. But here's actually another way that we can do it, and the pattern is fairly easy. So if I want to come up with, maybe I'll do a line of working out here. So if I want to come up with the I component, so what goes in here? Well, if I cross out that line that contains the I components there, then the I component comes from taking the product of those two minus the product of those two. So I'm kind of cross multiplying the other ones. Now it's important I do them in the right order because I am subtracting and not adding. So I do need to do the product in this direction first. So that's negative 4 times 0, which is 0, and then minus the product in the other direction, so the product in this direction here, which is 1 times 3, which is 3. Okay, so product down minus product up. Now let me remove those so we can see the next bit fairly clearly. So to get the next one, let's pick a different color. When I want to get the J component, I'm going to cross out the J components there. And this time I need to go the opposite way. So I'm going to start off by doing the product upwards there. So 1 times 4, which is 4, minus, and then go the product downwards. So 1 times 0, which is 0. Alright, let's just rub out those again so we can see for the last one. So for the Z or K components, I'm going to cross out that row, and now I'm back to the original way, which was down first. So 1 times 3, which is 3, minus, and then going the other way, negative 4 times 4 is negative 16. So minus negative 16. Alright, so what does that give me there? 0 minus 3 is negative 3, 4 minus 0 is 4, and 3 take away negative 16, or 3 plus 16 is 19. So that would be, and just to be clear, this is a vector, that would be the same as what's saying negative 3i plus 4j plus 19k. Okay. Just before we finish there, I want you to see that, or how to do this on your graphics calculator. So there we go. Now you can access cross product and dot product through the menu, so you can go into your menu and access this, but sometimes it's just as quickly to type in the syntax, which is cross P. Same way as dot product is dot P. Then you need some brackets, and then you need the two vectors separated by a comma. So I'll need a 3 by 1 matrix there. So in this case, what my two vectors were? One were I minus 4j plus k. So that was the first one there. Then I need a comma, and my second one there, so again a 3 by 1, and my second one was 4i plus 3j, so I need a 0 there, and then hit enter, and there it is, negative 3i plus 4j plus 19k. Okay, so I think we'll leave it there for this video, and then I'll do another short one just with a quick other application of vector product.